So welcome to the section of lightning talks. So everyone will have 6 minutes, and it's called lightning talks because if you go over your 6 minutes, you'll be struck by lightning. So let's get started. First talk is, I guess, Michael Block.
Well, just in case for the speakers,
right.
It's being recorded. If you're not happy, you can just signal it later and we'll erase your talk. But the default is that every talk is being recorded, as usual.
We're getting a signal 5 seconds before lightning strikes, so we can actually end the talk.
Sorry.
Do we get a signal a minute before lightning strikes?
Sure.
Okay. So thank you very much to the organizers for letting me present in this lightning talk, where I will try to show you how we used this quantum processor that we developed here at UC Berkeley in the group of Irfan Siddiqui to store and process ternary quantum information, so 3-level systems. And then how we would like to use that to probe the scrambling of quantum information. So first of all, storing information and processing in 3-level systems, or quantum trits, Q-trits, it's more than just an extra level. There is a computational argument to do this. Hilbert space gets larger, you do this in a hardware-efficient way, and also you get a higher connectivity. So a network of Q-trits is more connected than a network of qubits. And especially in this time of noisy intermediate stage quantum processors, this might give you a nice benefit if you want to do faster computation. But moreover, you get some new physics if you look at Q-trits versus qubits. It's, for instance, the minimal system to study contextuality, which has led to this certified random number generator recently. And the physics that we are interested in today is that 2 Q-trits are the minimal system to implement what is called scrambling. And scrambling is really the rapid spread of quantum information from something local to all the degrees of freedom of the system. And it turns out that this scrambling is really playing a key role in a connection that has recently been being made more and more between quantum cosmology and quantum information, where we're seeing that physical phenomena such as black holes, the holographic principle, and wormholes really have an analog in quantum information in such a way that I, as a quantum engineer, can now talk to people who study this field and understand it kind of in the language of quantum information, error correction, and entanglement. And that's really something that I'm really excited about and that I like to study with the systems that we are working on. And in particular, I'll show you an experiment that we're working on to study the black hole information paradox in the context of scrambling. So the devices that we are working on are this 8-qubit or Transmon chip. It's a superconducting circuit where the qubits are nonlinear oscillators. In our case, we have 8 of them, aligned here as Q1 to 8. Each of them have their individual readout resonators. Our chip has the ability to couple all of these readout resonators to a single bus such that we can read them out with a single channel. And I couldn't agree more with the statements of the experimentalists 2 days ago to say that it's very important to quantify all your numbers and do metrology. In our case, we do randomized benchmarking. We do something very similar to state-of-the-art for single qubit gates. Our 2-qubit gates are now 95, which is probably good enough to do this experiment, but we have ideas how to improve it. So moving on to processing ternary quantum information, our quantum system is actually a nonlinear oscillator, so we naturally have this 3rd level, it's just usually people don't really use it. So we can excite it with a different resonant microwave tone. We can detect it in our readout resonator. We see in the IQ plane of the microwave field that we reflect off of it. We can single-shot read out the Q-trit state in 0, 1, or 2. We can turn on control pulses of variable length, and we can see that we can drive Rabi oscillations in a single Q-trit subspace. We can also quantify how well we can do gates, either in the 0-1 or the 1-2 transition to encode Q-trits. And what is nice is that we don't lose a lot by going to this 1-2 transition in terms of error. The error is very similar. So it really is a good coherent system that we can use to process information. And then what we have developed, which is new, is 2 Q-trit control. What we've implemented is a gate between 2 Q-trits. And this is an all microwave-driven gate where we turn on a microwave, and the effect of what it does is it rotates a target qubit in this Q-trit, in this subspace, depending on the state of the control Q-trit. So you get these oscillations that are different from the control being in 1 or when the control is in 0 and 2. And this is the kind of differential signal that we use to implement what I would call the canonical C0, but then for Q-trits. So only if the control Q-trit is in 1, we flip the target. And we can use this to make entanglement between our 2 Q-trits. Here we show density matrix of an EPR state, 0, 0, plus 1, 1, plus 2, 2. With a fidelity, it requires 2 Q-trit gates, and the fidelity is roughly 95%. So With this system, we now like to study scrambling. We have a decomposition of a scrambling unitary to compose out of two of our two Qtrait gates. And that's something that we're working towards. But in the final few minutes, I want to give you some intuition of what it would mean to have scrambling. What would you see? So a formal definition is that if you have a two-body system, and you see at how operators get mapped by a unitary U, and you want to check whether U is scrambling. It is scrambling if any single body operator on the first or the second system gets mapped to a many-body operator. So that's the spread of operation of information throughout the system. And the way that you could see this is by looking at a process matrix, but kind of plotted differently, called the Pauli transfer matrix, which looks at when you input a certain Pauli operator, to which operators does it map. So here's the input, here's the output. For a local gate, if you would do it on the first system, it would also say local here. An entangling gate would map some of these inputs to two-body operators. But a scrambling unitary would map every single body operator to a many-body operator. And that's the quantum process tomography that we would like to see and study. And the nice thing about our system is that we could really do this process tomography because we can do our measurements very quickly. Now, there's another way of quantifying scrambling, and that is by doing a circuit that Chris Monroe actually presented on Tuesday. The short version of it is that you create two black holes and you entangle them by a wormhole, and you can do this teleportation protocol where effectively the wormhole is implemented by a scrambling operation, and the protocol measures the out-of-time order correlators between these of the scrambling operation. And by measuring the success probability and the teleportation fidelity, you get a feel of how well you're scrambling, and you can compare this to how much decoherence you have in the system. So this is one of the protocols that we would like to study. There's much more links to high energy physics and other protocols that we could do with these Qtrits. So with that, I'd like to thank you for your attention.
Okay, thank you for a on-time finish. And so we have time for 1 to 2 questions, depending on length. Yep.
Are your errors symmetrical, the 0, 1, 2? Like do you have bit flips, or is 0 more robust than the 1 and 2 states? Or?
Yeah, so our errors are not symmetric. 0 is more robust in terms of energy relaxation, and also actually in phase noise. So the second level is more susceptible to charge noise. So we both have more T1 errors and more T2 errors in our second state. Yeah.
Another question? Okay, let's thank Napoleon.
Is this working? Good.
Next talk, Adam Bulan.
Great, thanks. This is joint work with Bill Pfefferman, Chinmay Nurki, and Umesh Vazirani. So as you know, one of the near-term goals of our field is to establish quantum supremacy. That's a practical demonstration of a quantum computation that's very difficult for classical computers to reproduce. And demonstrating this kind of requires that you find some form of computational task, which is both feasible in the near term, has strong evidence for hardness from a complexity theory standpoint, and is also verifiable, at least on near-term devices. So one of the first cracks at this problem was the boson sampling proposal of Aronson and Arkhipov. And they had this very nice insight that you can establish quantum supremacy by making a certain hardness conjecture. The hardness conjecture says something like it's sharp p hard to approximate most output probabilities of some randomly chosen quantum systems. And what made this conjecture so compelling from the optical standpoint was that for linear optics, it is known to be sharp p hard to exactly compute these quantities on average. This ends up coming from the fact that in linear optics, output probabilities are related to permanence, and permanence have a form of average case hardness based on a classic result of Lipton. So the only remaining step to complete the complexity theoretic proof of supremacy here is to robustify this average case hardness result and make it more robust to small amounts of error. So if we were to, plot proposals at a very high and broad level, in terms of the how standard are the complexity assumptions, how feasible are they in the next, let's say, O of 1 years, I like this phrase now, and how easy is it to verify a near-term device, this had very strong evidence for hardness and looked like it could be feasible in the near term, so this is part of what launched the original quest for experimental supremacy almost a decade ago. So kind of what happened since then is there's been great advances in the development of, say, superconducting qubits and many other systems. And it looks like we'll be able to implement random circuits over qubits of a substantial size in the next O of 1 years. So you can establish supremacy for these devices by conjecturing, it's hard to compute most output probabilities of these randomly chosen qubit circuits. But this conjecture has a gap that was not present in boson sampling. Namely, that exact average case hardness is not known for these systems. And this is just because they aren't as closely related to permanence. And without this form of average case hardness, there's not strong evidence that this is kind of a hard distribution to reproduce classically, that these generic interference patterns of qubits cannot be reproduced classically. And also without this form of average case hardness, you don't have a hard distribution to test your device against. Like if you were trying to show to me you have a 3-sat solver that solves 3-sat in all instances, you kind of need a hard distribution to test it against. You need to have some evidence that that's hard. So our main result is we fill in this gap and we show an exact average case hardness for computing amplitudes of random circuits over qubits. And just as in boson sampling, in order to complete the proof of supremacy, you would still need to robustify it. So if you were to plot random circuit sampling on this high-level plot, say prior to our work, the complexity assumptions were maybe not as strongly supported as boson sampling, but it was kind of designed with feasibility in mind. And our work brings it up to the level of boson sampling in terms of our strength of evidence, a belief in these complexity conjectures. Possibly even plus epsilon. I say this because they're also known to have a property known as anti-concentration, which is conjectured for boson sampling, and there's great numerical evidence for it, but not yet a proof. We also question to what extent it's actually to what extent it's possible to verify these random circuit sampling tests. So some of the leading candidates for verifying these near-term systems are called cross-entropy and heavy output generation. And they all take a few samples from the device and perform some statistical test on those samples and accept if it's sufficiently close to the ideal. So clearly scoring well on these tests is necessary to be doing the right thing. But it's natural to ask, is this sufficient as well? Like, is it also sufficient to verify supremacy through these sharp P hardness arguments I mentioned before? And one thing that we notice is that actually if you believe in certain noise models, you might be able to believe these actually do connect to these sharp P hardness result. So in particular, we show that for cross-entropy, if you score very well on cross-entropy, and you believe the entropy of your device is higher than it would have been in the ideal system, then your output distribution is actually close to the ideal and does certify supremacy in this way. And this assumption could make sense if you believe in certain types of noise, like say depolarizing noise. If you believe in other types of noise models, it might not make sense. So I think that this could give you a potential way to believe in verification of this strong measure of complexity in the near term. We also give a sort of optimal verification test, which verifies both cross-entropy and Hogg, which I don't have time to discuss. So yeah, so in short, depending on how you believe in these assumptions, you might actually believe RCS could be verifiable. And I'll just conclude by saying, there's many other things you could do here. As Scott described, this heavy output generation scheme allows you to make stronger assumptions and get easier verification. And I'm about to be struck by lightning, so I'll end. But there are other things one can do. Thanks.
There's no give in that entropy inequality? It has to be greater than?
Oh, yeah, it could be greater than or epsilon less would still work. Yeah. This is just from Pinsker inequality. It's very, very simple. Yeah.
Are there questions?
Along the same lines, you said if the cross entropy is epsilon close to the correct cross entropy.
Yes.
So how many samples do you need to take in order to get epsilon? Just one by epsilon?
Polynomially close is plenty. In fact, there actually should be there should be exponential convergence in estimating the cross entropy from samples because.
My other question is how is cross entropy sensitive to noise? So if I change a distribution in statistical distance by delta, how would that affect to cross entropy? That could completely mess it up? Or?
Oh, in terms of you mean the ideal one?
Right, yeah. Suppose that I sample delta close signal 1 to ideal. Does that imply that the cross entropy is with respect to statistical distance?
I believe so. Yeah, I believe so. Yeah.
That's just because if you just sample for
this might be some event or something.
Well,
Yeah, sorry, go ahead.
in this case, the fact that the ideal distribution is not very far from uniform, that should make because you're.
Okay, but entropy can change a lot when you change the statistical distance by a tiny bit.
No, I know. That's what I was saying. That.
But yeah, because this thing is already kind of uniform-ish, that it's you're kind of staying in the high entropy area even if you change it a little. So.
Okay, let's thank Adam.
Adam, I think you were too generous to Hogg when you said verifiability is great. I mean, it still takes 2 to the n time.
Oh, sure, but that's essentially so does every scheme.
Yeah, right,
Yes.
right.
So that we know, and other than the interactive.
Yeah, yeah.
So.
Okay, our next talk is Computation Huang.
Hello everyone, I'm Computation Huang and I'm a grad student in University of Michigan. And right now I'm a research intern at Aliyun Quantum Lab. And this is the joint work with my colleagues Michael Newman and Mario Segedi, who I didn't see here. I don't know where he is. Anyway, so the problem we're looking at is strong quantum simulation, which is using classical computational power to simulate, or more specifically, given a poly-sized quantum circuit C and output string X, we want to classically compute the amplitude on this X component. And this is in contrast to weak simulation, which is more close to supremacy, where we want to sample from the distribution given by the circuit acting on the all-zero string. And it is not hard to see that strong simulation is Sharpie hard, at least if you want to do it exactly. But Sharpie hard doesn't tell us too much information about how exactly hard this problem is. And to prove such a lower bound result, one can start from some complexity assumptions. So there's a full hierarchy of assumptions we can make and results we can get. For starters, if we have no assumptions, then proving anything meaningful would lead to Sharpie not equal to P. And on the other extreme, if we assume that there is a lower bound, then there is a lower bound. We're not proving anything really meaningful. But for some people, very paranoid or think that pH would collapse one day or just tomorrow, these things might not be very attractive to you. So here is our result. We're saying that here are these prominent, most widely used classical strong simulation methods. They are so naive, and here we call it monotone for reasons we'll explain later. such that for this regime of strong simulation method, we can prove unconditional explicit lower bound. Unconditional meaning that there is no complexity assumption needed, and explicit means there is no constant factor and there is no asymptotics. So what is a monotone method? A monotone method, so there are these 2 points. The first one is it treats the quantum circuit as a tensor network. More specifically, each gate or each state is just a vector or matrix, or even fancier, a higher rank tensor. And it only involves addition and multiplication on non-zero entries of the tensors. So here's a very simple example for the circuit presented on the left. For a monotone method's perspective, it just looks like this. What the non-zero entries are doesn't matter. It will just perform addition and multiplication on these entries. Okay, so our main theorem is saying that there is a reasonably sized circuit with linear width and Pauli depth such that such a circuit cannot be simulated efficiently by any monotone method. And the proof sketch is that, so in order to do this strong simulation using monotone method, we are disregarding what the properties these gates can have. For example, if they are from Clifford group, then we can just use Gauss-Neo to simulate them pretty efficiently. So here, we're actually doing something much stronger. We are trying to use a monotone arithmetic circuit to compute a multilinear polynomial, and that polynomial could as well be permanent. We constructed a kind of artificial circuit which can have the potential of computing permanent using a monotone arithmetic circuit. And like 30 years ago, it's already proven this is not possible unless the circuit is of exponential size. Okay, so why is this useful? The first reason is obviously most of the widely used strong simulation techniques proposed by many former results and even computation, industrial packages follows in this regime. For example, Schrödinger and Markov-Xi are 2 ways of contracting a tensor network. And fancier, we can use Feynman path integral, or even Aronson and Chan's technique of making use of Savage's theorem. So it's and it also provides us a very interesting byproduct, which is the monotone arithmetic circuit computing permanent in time and square times 2 to the n, which is not known before. So naive algorithm would take n factorial, and Savage's theorem would bring it down to 4 to the n, but 2 to the n is not known before. This almost matches the state-of-the-art non-monotone method. Of course, this is just a worst-case lower bound. We believe that average-case complexity is provable, but we haven't done it yet. So our main take-home message here is this. If we want to push the classical simulation ability further ahead, then one needs to focus on non-monotone approaches. There are slightly non-monotone approaches, such as Stossen-type fast matrix multiplication, which gives you a polynomial advantage. Or there are very non-monotone ones based on Gottesman and Neo theorem, basically saying if it's not far from a Clifford circuit, then we can still do it efficiently. But it's just a completely different approach. That's it. Thank you.
Questions? Yeah.
I would like to ask you to clarify what is exactly a monotone circuit. Is it a circuit that only can do arithmetic operations on the input elements of the tensor, or what is exactly the definition?
Yeah, monotone arithmetic circuit is a circuit where the gates are only addition and multiplication. So you cannot do subtraction or division.
Can you prove time-space trade-offs? Like, could you show, maybe hope to show that like we got the optimal trade-off, or that we didn't get it?
That's a very good point. Here, we're only proving the total time. We didn't consider parallel time, for example. Yeah. But I think it's safe to say that under this regime, you cannot do up to 100 qubit. even if there isn't parallelization.
Yep.
What if I'm just interested in an approximate solution?
Yeah, that's another very good point. So there are these things we need to explore to try to further push the boundary, because but right now there's no way of making use of truncating error to make it more efficient.
Okay, let's figure it out.
So it didn't make use of diving into precision. On the elementary pre-print, every elementary gate takes time.
Okay, our next speaker is Dawei Ding.
Hello everyone, I'm Dawei Ding, currently a PhD student at Stanford and also doing an internship at Alibaba this summer. And this is going to be a talk about noisy feedback and loss unlimited private communication. Some work done with Saikaku-ha, Arizona. Okay, so the thing is that many cryptographic protocols involve the use of a public side channel. For example, in BB84, Bob and Alice are using a public side channel to talk about which bases I measure in, which bases I prepare in, and therefore this seems to be a key part of a lot of these protocols. And these are public side channels, so the eavesdropper can also listen in onto this side channel. The thing is that this side channel is assumed to be perfectly noiseless to all parties. So all parties have access to a side channel, and it's perfectly noiseless. This is usually assumed for simplicity. You can also argue that if there is some noise in a side channel, you can use error correction to get rid of the noise. But what we ask in this paper, in our project, is to say, is this actually okay in all circumstances? So one thing we could ask is, for example, in the continuous variable case. When you go to a continuous variable case, your public side channel becomes a continuous continuous variable classical channel. We basically can send real numbers with zero noise to each parties. This is known in classical information theory to have infinite capacity, even if you have a power constraint, input constraint onto your inputs, a power constraint onto your inputs. And this is the non-zero case where you have infinite capacity is completely different, the perfectly zero case is completely different from the non-zero error case. So this kind of goes against the argument we had earlier about error correction, bringing the error down. It can bring the error down, but never go to zero. And these two cases can be completely different. So what we ask in our paper is, okay, let's take the usual setting for private communication, but let's add a little bit of noise. So this is the following setup. So Alice has some quantum channel phi, and she sends it over some large number of uses of a quantum state phi. And then she sends it over some large number of times of quantum channel. And then Eve can also eavesdrop on this quantum channel. And then Bob can also send classical information back through this feedback loop. And Eve has access to this feedback communication, but on the initial round of communication, Eve gets a little bit of noise on that feedback. So if you take out this part, this becomes the usual way of looking at private feedback-assisted private communication. So we're saying, okay, let's take a look at this slightly altered model, and let's see what happens, what thing changes. So what we showed is that for the case for the pure loss channel, which is a quantum analog of the additive white Gaussian AWGN channel, for this case, if you look at the conventional model, where there's this noiseless feedback throughout, we have an upper bound of capacity of negative log 1 minus eta, where eta is the transmissivity, or basically the loss in that channel. The thing about this capacity is that it's loss limited. So usually when you look at capacity expressions for continuous variable channels, you have a power constraint on your input. You can't send any input. And then your capacity then becomes a function of that constraint. But in this case, even if you do not have a constraint on your input, you have some finite upper bound on your capacity. And we call that loss limited. So this is actually a very pessimistic result, because it says that QKD, you can't have very high capacities even if you have a lot, use a lot of power on your communication. So in our model, we add a little bit of noise to Eve. What we get is some new rate. This expression, the only thing that you need to notice is that there's an NS, and this is the input power constraint. And when you take NS to infinity, which is saying that you have no input power constraint, this becomes infinite. So this goes from loss limited to loss unlimited. And that is a big difference. And that is all achieved by adding just a little bit of noise to Eve's copy of the feedback on just one round of this protocol. So maybe I went a bit fast, but the main message is following. If you have some CV, continuous variable cryptographic protocol, the side channel is some noiseless classical CV channel. If you add a little bit of noise on one round, you get a completely different rate of communication achievable on that channel. And this shows a sensitive dependence on your communication model. So basically, a lot of the treatments, theoretical treatments of CVQKD or private communication, our main message is to say that you have to be more careful. You can't just naively assume this public side channel is noiseless. And that is it. Thank you.
Okay, I'm going to ask the first question.
Okay, sure.
So as I understand, you didn't have any noise from Bob to Alice.
Yes, that is correct.
I mean, so in these noiseless channels, there's already results that even without a quantum channel, you can generate key.
Even without a quantum channel, you can generate key. Yes, true. Mm-hmm.
Okay, so but this is more than say the sum or something like that.
Okay, so in the classical setting, you can generate key through a noiseless channel with feedback, right? And no feedback.
When there's noise in it.
When there's noise in there's no feedback, nothing else.
I think there's feedback as well.
Feedback as well, yeah, that's true. That's true. I'm not saying quantum channel is a key component of this analysis. This also induces a classical result as well.
Great.
Yes.
Other questions? Okay, thanks.
Connect yourself to the microphone, otherwise the microphone. Yeah, all right, fine.
Next is Scott Aronson.
Hey.
Hey.
Okay, so I want to tell you about shadow tomography, which is a paper I wrote that's going to be at Stock a couple weeks from now, and then some new work with Guy Rothblum, which is not out yet. Okay, so what was the problem that I called shadow tomography? So what it says is you have there's some unknown mixed state rho. Okay, let's say it's d-dimensional, and you can get some copies of rho. Okay, so you have access in your lab to rho sub k. Okay, now, ordinary tomography would say just learn the density matrix of rho, approximately by measuring these copies. And we know that that requires something like d squared copies. In fact, there were some breakthroughs a couple years ago where it was finally established that ordered d squared copies of rho are necessary and sufficient for tomography. Okay, but now let's suppose that we have a more limited goal. You know a list of 2 outcome measurements, E1 up to EM. So you say they're POVMs, right? And your goal is just, for each I, you would like to know the approximate value of trace EI rho, right? So for each of these measurements, what's approximately the probability that it accepts rho? Okay? Well, then a couple years ago, I posed the question, how many copies of rho are needed to do this? Okay, let's ignore for now computation cost. Okay, clearly, d squared copies are sufficient because you could just do full tomography. At a different extreme of parameters, something like m copies of rho will also clearly suffice because I could just apply each EI to separate copies of rho. Okay, but for various questions, quantum money, quantum copy protection, it was relevant to know, well, could you do this using a number of copies of rho, which is polylogarithmic in both D and M? Okay, so even, to learn an exponentially large state on exponentially many different 2 outcome measurements, could we do that using only polynomially many copies of the state? Okay, so I conjectured that this was probably not possible. I could not rule it out, and now I know why I couldn't rule it out, because it's possible. Okay, and so well, this was in the Andres Gillian's talk yesterday. Okay, but so I gave an algorithm that does it with like this number of copies of rho. Okay, whereas the only lower bound that I know, by the way, is this, which holds even in the classical case. Okay, and so then this implies, for example, that any scheme for quantum money with a small key, or any scheme for quantum copy protected software, will require computational assumptions. It cannot have information theoretic security. Okay, and this has various other implications. Okay, now a year ago I gave a talk about this, and Guy Rothblum was in the audience, and he said, well, this, okay, so to prove this, you have to sort of measure your copies of rho very, very carefully to avoid damaging them too much, right? I won't have time to go into, how the protocol works. It involves, sort of combining 2 ideas. One is called, post-selected learning of quantum states. And the other is called the quantum Orr bound. And this is like a type of sort of gentle measurement that doesn't disturb states by too much, right? Which is clearly needed here. And so then Guy said, well, this whole gentle measurement, this sounds a lot like differential privacy. Okay, what is that, right? Well, this is, how much time?
A little more than a minute.
All right. Differential privacy is a subject where you look at algorithms that sort of query a database with n entries, and you impose the requirement that the algorithm does not reveal too much about the data of any individual user. So say if we have 2 databases, X and X prime, that differ in only a single entry, then we say the probability that the output is Y under database X has to be like at most 1 plus epsilon times the probability that the output is Y under database X prime. Okay, and the way that you achieve this tends to be things like, add some random noise to the result of the query before you return it. Which, interestingly is the same kind of thing that you do to get gentle measurements in quantum mechanics, right? You just sort of add some like Gaussian noise to your, answer. You can avoid damaging your state by too much. Okay, so I said, okay, but this is probably just, you can connect anything to anything else. All right, long story short, there is a connection here. We can prove it. It goes in both directions, and we can use this connection to improve the shadow tomography. I believe we can get this 4 down to a 2 by taking known results from differential privacy and porting them into this setting of gentle measurement. Well, thanks.
Questions?
do you think that the quantum techniques can give back something to differential privacy?
That would be awesome. We thought about that. We don't have an example, but that would be awesome if we could do that.
Any other questions? Okay, thanks, Scott, again.
Yeah.
Okay, next talk is Abhinav Deshpande.
Hi, I'm Abhinav, and this ongoing joint work with Bill Pfefferman, who is here in the audience, Jim Garrison, and Alexei Goshkov at Quix at UMD. So the motivation is that a lot of work in physics is actually classification, such as like we have phases of matter, where people are interested in knowing whether ground states are ordered or disordered, and people are interested generally in long-time behavior of states as to whether states thermalize or not, and whether there are other exotic forms of like non-ergodicity breaking, like localization of pre-thermalization, and whether there's topological order, and like whether a state is topological or not, and if it's not, then what's the relevant symmetry class that applies. But since I'm here at Simons, I'm talking about complexity theory. So complexity theory gives a natural classification of problems into easy or hard. And what we want to do is see whether this kind of classification can be useful in physics too. And one question that we ask is whether tools studied in the context of quantum computational supremacy can be applied to physics, but not necessarily with the same goal in mind. So we're not necessarily trying to falsify the extended Church-Turing hypothesis. Okay, so I'll now go into some brief background about projected entangled pair states, which are also known as PEPs. So these are analogs of matrix product states in 2 dimensions. And like matrix product states, they are good Ansätze for ground states that satisfy area laws. And like, however, one caveat is that they are sharply hard to contract in general. And so the key idea behind that proof is that PEPs can represent output states of post-selected quantum circuits. So in that figure, here's a general quantum circuit, which acts on an input state and some ancillas in registers X and W. And in this register, you measure and condition on the output being a particular string that you want. And the state appearing in this register Z is what I call an output state of a post-selected quantum circuit. So now this result by Schuck and others can be reinterpreted in the modern times in the following sense, that PEP sampling is hard. So what's PEP sampling? It's the problem. So here's a black box that, given a description of a PEP state, samples from that state in, say, the computational basis. So now what we can show, essentially what Schuck and others showed, is that with this box, you can solve PP problems in polynomial time if you make polynomially many queries. So you can earn money from that. Or more formally, PP is in BPP to the O PEPs. So this implies that if one could feasibly build a PEP sampler, then PP equals BPP, which is very unlikely. And this result straightforwardly can give you a result for hardness of approximate sampling. So now, since we want to make the connection to physics, we use this result by Perez-Garcia and others, which shows that any PEP state is arbitrarily close to the unique ground state of a spatially local Hamiltonian. So as a corollary, we can obtain something like this, that there is a class of local Hamiltonians for which it's not possible to approximately sample from the ground state, and even quantumly, unless PP equals PPP. Because nowhere here did I assume that the oracle was classical or anything. Okay. So, yeah, the preceding reason is why this is not a proposal for quantum computational supremacy, because we don't have a quantum sampler, and the hardness result applies even quantum mechanically. We also get some robustness to total variation distance errors. And so as of now, this result just applies to parent Hamiltonians of a very specific class of states. There are output states of post-selected quantum circuits. So one problem is whether we can make this more natural in the sense of whether it can give more restricted Hamiltonians for which the hardness result still applies. Also, this result does not assume anything about the gap, and it can be arbitrarily small in general. And any improvement on this seems unlikely unless these two classes are equal. Here, p to the QMA log is when you have access to a QMA oracle, and you can call it logarithmically many times. So now, yeah, this work and preceding work by Ben show that p to the QMA log is actually in PP. Okay. And one other question is whether we can use some sort of classification for other classifications via more standard means, such as the problem of computing ground state energies of Hamiltonians. So that's more like that's relating with the QMA and QCMA literature. And yeah, once we have that, we can ask the question like, which states are classically easy or quantum easy and quantum hard, and whether there are phase transitions between them. Yeah, that's it. Thanks.
I have a very quick clarification question. Can you go back a couple of slides? I think you implicitly used something that I just want to make sure I got it right. So, okay, I forgot which slide it was, but you were saying that there's a theorem that says that given a PEPS as input, it's hard to sample from the distribution that takes in there.
Yes.
And then you use that to deduce a theorem that says that given a local Hamiltonian as input, it's hard to do sampling.
Yes.
So that uses that you can compute, the reduction uses you can compute the local Hamiltonian from the PEPS efficiently.
Yeah, you can construct a local Hamiltonian that's a parent Hamiltonian of the PEP state.
You don't need to contract anything, you can just do it.
Yeah.
Any other questions? Okay, let's think again. Okay, next speaker is Jonathan Twati.
Okay, so I want to talk about
circuit complexity lower bounds for homological codes. And this is a joint work between David Aronov and myself. Okay, so first off, why are we even looking and interested in circuit complexity? Well, it is well known that in classical computation, lower bounds on circuit complexity are very hard to find, and they are also a very good metric of how complicated the calculation is. And also in the quantum setting, we have a lot of different kind of domains where we are interested in finding such lower bounds. The first two that I can think of are in the QPCP conjecture, the quantum QPCP conjecture, and also in the NLTS conjecture, which are both very interested in showing that some states are non-trivial, when triviality is triviality of a quantum state is just, is the quantum state, can I generate the quantum state with a constant depth circuit? And we are interested in ruling out some states and showing that they are complex in this sense. And also in multipartite entanglement, we are interested in finding such lower bounds. So let's look at the kind of methods that we have today that are known to show this kind of lower bounds. So the first method that I can think of, okay, is what I would call the correlations method. So what does it mean? Well, if you look, the easiest example you can think of is if you have a cat state, okay, say 0 n plus 1 n, and you want to show that this state is, you cannot generate this state with a constant depth circuit, then you can just look at two different qubits, okay, and look at their light cones. And you can just say that if you assume by contradiction that you can generate cat plus using a constant depth circuit u, when d of u equal 1, then then you can see that the light cones of every, if you look at the computation going this way, and here you have your qubits, okay, and here you have the input qubits, then you can see that the light cone of any given qubit here is going to touch a constant number of qubits on the input layer. And therefore, if I look at, I can also always find another qubit here that whose light cone is going to be completely disconnected from this one. And in this situation, we expect those two qubits to be completely uncorrelated, but they are obviously correlated, and this is a contradiction. The same type of argument is used, is actually the most general generalization of this kind of argument is Lie-Robinson bound, which also gives a logarithmic lower bound for circuits which are generated, for states, for generating states that come from Hamiltonians that are gapped. And recently, more recently, Eldar and Rowe have proved, used the same type of argument to show, a generalized version of the NLTS conjecture. So this is the first method, and we have another method which is just looking at a state and saying that, okay, if this state is part of a quantum error correcting code, and if the distance is L, then obviously any two states, orthogonal states inside this ground state are going to be to agree on reduced density metrics on less than L qubits. And you can use this fact in order to achieve the same kind of lower bounds, but I don't have time to show it now. So what is known for homological codes? So for homological codes, we have a very beautiful and geometrical proof of Bravey, okay, who showed that in some interesting regime, which I would call the geometrical regime, which means If I reduce myself to look at only at circuits that are geometrically local in the grid of our topological code. So, for example, if you have a toric code, that we have the grid of the toric code. Yes, and now we can ask whether I can build the ground state of this code using only geometrically local gates, which are not only local in terms of the number of qubits every gate acts upon, but also in terms of the geometry of the gates. We want the gates to act on qubits that are close by in the grid matrix. And in this case, Bravi showed that we have a lower bound, okay, of square root of n. Okay, so we need omega of square root of n depth to generate this kind of topological ground state. And the basic idea, if I have time for this, is to look at two. I don't have time for this.
Your time is basically up.
Okay, so I will just state our results. I don't have time to state our results.
State the results quickly.
Okay, so to state our results very quickly. Yes, so my result is like this. We prove that if we are looking at generating the ground state of the spherical code, which is the same as the toric code, but we don't use the topology. The homology groups are just vanishing. So we can't use the same type of arguments that we used in order to prove that states inside the quantum code, error-cognitive code, are difficult to generate. Here we don't have this power, but we can still prove the same kind of lower bound. What we do prove is that in this case of non-geometrically local circuits, we get a lower bound of log n, and in the case of more general surfaces that don't need to look Euclidean, then in association for another topological conditions that we are not going to speak about now, we get double logarithmic bound for generating these states. And yeah, that's it. Thanks.
So, do you expect the log to be tight or the square root?
This one?
Yeah, kind of.
Well, actually, it is tight, because if you look at surfaces that are not behaving in an Euclidean way, if you look at something that is more like hyperbolic plane, then this logarithm is, you can do better than this logarithm. This is like tight. Yes.
But the log is not.
But then the log also is tight.
Any other questions? Okay, let's thank God again.